All right. Good evening, everybody. Hello. Thank you for joining us. My name is Stephen Hummel, and I'm joined tonight by Saul Rivera. Hi, Saul. And we are located in far west Texas at the McDonald Observatory. Tonight it is a cold night. It's December. Winter's basically here, and that has me thinking of some of the beautiful mountain scenes we get out here in West Texas. Sometimes this one was taken last year. Um, and in the snow with the Hobby Eberle telescope there behind that tree in the foreground. So I'm showing this picture because, it's not always clear here, and some of you could probably already guess by the fact that if you've watched this program before, usually I don't have the lights on. But it is cloudy tonight, and in fact, I saw a couple snowflakes earlier. So it's cold, and against every forecast, and against what actually some forecasters say it currently is right now, it's totally cloudy. But some websites say it's totally clear. But I trust my eyes, and I also trust this camera here. This is a live weather feed from top of Mount Locke here at McDonald Observatory. And you can see it's 24 degrees. It's pretty cold. It's Fahrenheit. And those aren't stars in that image. Those are just hot pixels. So what you're staring at is a bunch of clouds. So unfortunately, the weather is not cooperating tonight. But that is okay. We do have a plan. We have some plans. And we are going to take a look at some astronomical objects with previously taken images and discuss them, kind of like what we would be doing with live images. We're just going to do that with previously taken images. And that's the plan for tonight. So we got a lot of cool stuff lined up for you. But Saul, why don't you go ahead and introduce yourself, because this is your first time appearing on a live internet feed.
Yeah, so hi, my name is Saul Rivera. I'm a public affairs specialist at the visitor center here. I'm actually one of the newer hires, only been here for a little over a year now, and I'm a graduate from UT Austin with a bachelor's in astronomy, and I actually got to work out here as an intern before I got hired full time. And this is really exciting to be in one of the live programs. So throughout the program, something I want to let you all know, if this is by chance your first program, we do have moderators in chat who are ready to answer any questions you might have. If a question might need some more detail or might be better suited to what we're viewing at that moment, the moderators will send that along to Stephen and I, and we'll either answer it right then or at the end of the program. And kind of talking about the program, I'll pass it back over to Stephen so he can talk a bit about the telescope.
Yeah, so this telescope right behind me is a 16-inch telescope that refers to its diameter, its light gathering area. The bigger the aperture, bigger the diameter of the mirror in the telescope, the better the image generally will be. The more light you gather, and the higher the resolution. So it's 16 inches. That's 0.4 meters. And I'm going to be showing a lot of pictures previously taken with this telescope. If I don't specify otherwise, then the picture was taken with the setup we would be using tonight for the program. So we also have a camera mounted on the back. If it does clear up, and there is a little bit of hope that it will clear up tonight, we will be using this telescope for some live views. But when we see those live views, there will be no color in the image because I am not using a color camera. Is a black and white or monochrome camera, because those tend to be much more sensitive than the equivalent color camera ever could be. So that's the telescope behind me as well. You can see it here. So we're going to hopefully get some views through it, but if not, that's okay, because I've spent a lot of time with this telescope, and I've got lots of pretty pictures with it. But tonight, what we are going to talk about is essentially our Milky Way, and more generally, our local group of galaxies, our kind of family of galaxies. So to kind of introduce that topic, I'm going to let Saul take it again. So Saul, if you'd like to introduce us to what exactly the Milky Way is and what it's all about.
Yeah. So, kind of before we go more into all the other galaxies, let's talk about the one we live in right now, the Milky Way. So here we have an image from Justin Pautsky, one of the people that works at the Hobby Eberly Telescope here at the observatory. A picture he took of the Milky Way above the observatory. So the Milky Way is what appears to be that kind of bright, cloudy structure arching over the sky. And another view of it, here's another image, also taken by Justin Pautsky, of the Milky Way above the Jeff Davis Courthouse. And finally, how about we see it from an even different view, from top down? So this here is an artist's rendition of the Milky Way. Due to that, we can't go far away enough to get a picture of this type. And the Milky Way is a galaxy, more specifically, a spiral galaxy. So a galaxy is a system or a group of millions or billions of stars that, along with gas and dust, is held together by gravity. And our Milky Way is actually a pretty big galaxy, at about 100,000 light years in diameter. So let's say you want to take a weekend road trip and drive from one of the Milky Way all the way to the other. It will take you, so with that distance, first let me talk about how big a light year actually is. A light year is a unit of distance that we use for space. Is how far light can travel in a single year, which is about 6 trillion miles. So with that in mind, to drive from one end of the Milky Way to the other, going at 100 miles an hour, it will take you about 684,462,696,783 years to complete that trip. So make sure to pack all the snacks you can, all the movies, and make sure to not drink that much water because there won't be that many bathroom breaks. And speaking of the Milky Way, one of our first targets for tonight is something actually that's in the Milky Way. And I'll pass it back over to Steven.
Yeah, so when you look up, you see the Milky Way in the sky. Not tonight, but in the corner, this is a live view of the sky, and you can see, not many stars. But if those clouds weren't there, you would see the band of the Milky Way stretching across in the north. So this is the software used to control the telescope. And the first target we're going to talk about is called the Bubble Nebula. And the Bubble Nebula is located in the constellation of Cepheus, the king, which is located here, and Cassiopeia, the queen, which is to the right between the queen and the king. And this is a particularly dusty and busy region of our galaxy, of the Milky Way. I say ours, it's a bit presumptuous. It's not really ours. We just happen to live in it. It's the galaxy we live in. But the Bubble Nebula is aptly named. So this is a color picture I took with this setup. What was it? A couple weeks ago? No, a little bit, maybe 3 weeks ago. And this obviously is a bubble. And what we have here is a star-forming region. And star-forming regions are very common within the visible band of the Milky Way, within the dusty and cloudy bit. And within that, what that dust and stuff is mostly hydrogen, as well as other molecules of and things like carbon monoxide, dioxide, and all manner of things. But by far the most abundant thing is hydrogen. And when hydrogen is energized, when it gets really excited in the vacuum of space, it can sometimes fluoresce if there's enough energy. And when it fluoresces, the most common color it emits by far is red. It's kind of deep red. And so that's what we have right here. We have a glowing cloud of hydrogen, and the source of the heat and energy responsible is the star right in the middle. And this is a very large, massive star. This star is much closer, which is why it's brighter. But this one is about 5,000 light years away, which is a healthy distance, but not all that far in the grand scheme of things. But this is a O-class star. We're kind of on the border between O and B. And if you're not familiar with what that means, there's sort of a system of ranking the size and temperature of stars. And at the top of the chart is O, and second is B. And you may think, gosh, that's a really weird way of doing things. Well, originally they classified it A, B, C, D, and then they realized they actually had it all completely out of order, And rather than renaming it, they just rearranged the alphabet. So there's a whole story behind that. Anyway, this is an enormous star, many, many times the mass of the sun, much hotter and much younger. And generally speaking, if you have a massive star, it's going to be young, relatively speaking. This star is maybe a few million years old, and it's still sort of in the neighborhood in which it was born, because stars are born from these clouds of gas. But this particular star is much more massive than any of its siblings near it, and it's so massive and energetic that it's sort of it's pushing material away from it from the heat and energy or stellar winds that are coming off of that star. So as that heat and energy and all the materials being accelerated away from it hits the surrounding cloud of gas, gas and dust that it was formed from, it's pushing it back and forming a bubble. Now you may be thinking, wait a minute, the star isn't in the center of the bubble. It's off to the side. Why is that? Well, it's because it is more dense on this side. There's more material here compared to this side. So it had an easier time pushing material out in this direction, whereas it's encountering more resistance here. And also because there's more material and it's closer, there's more material to reflect light or be ionized, and that's why it's brighter in that region. And it is a true bubble. If you were to view this from a different angle, it would still be a spherical shape. It's something you often see in star forming regions. You have these kind of caves or bubbles or pockets being swept up or pushed out by energy from these massive stars. We're going to come back to massive stars later on too when we look at some of the other targets. But Saul, back to you.
Yeah, so before we go bit into some of our other targets, it's time to answer the big question. Where are we? So, as Steven said, right now, TN9, the other moderators, are in West Texas, which is located in Texas, which is located in the US, which is located on Earth, which is located inside of the Milky Way. So right now, if you want, you can start taking your bets of where exactly in the Milky Way we are located. I would say we will give out prizes, but sadly, I don't think we're allowed to do that. But now's the time to see if you're right or not about your guess. The solar system, Earth, the sun, all of that is located right about here, right where this little arrow is. So the solar system is actually located about halfway between the edge of the Milky Way and the center of the Milky Way. More specifically, we're in what's known as the Sagittarius arm of the Orion Spur. And the object we were just looking at, the Bubble Nebula, is located pretty nearby in the Perseus arm, right about kind of to the bottom left of where the red arrow is. Let's see. Oh, my mouse is acting up a little bit. Sorry about that. Uh-oh. And Milky Way isn't the only big galaxy that we know of. Far from that, in fact. There's a much larger galaxy nearby called the Andromeda Galaxy. So the Andromeda Galaxy is actually large enough and close enough that's visible with the naked eye. So in this image, we have the Milky Way over in a nice dark sky, and to the left of the Milky Way, you might see what looks kind of like a bright disk. That disk is the Andromeda Galaxy, and it takes up a very large portion of the sky. In fact, it takes up about 6 full moons of the night sky, which isn't an exact form of measurement, but it's good for our usage. And the reason that the Andromeda Galaxy looks so big in the sky is that it's super close to us at about 2.5 million light years away. Now, that sounds really far away, considering that 1 light year is about 6 trillion miles. But in terms of the cosmic scale in galaxies, the Andromeda Galaxy is extremely close to us. And how about we take a closer look at it? Back to you, Steven.
Yeah, so in terms of where it is in the sky at the moment, it is located in the kind of east-northeast. from here at McDonald Observatory, and it is in the constellation of Andromeda, hence the name, the Andromeda Galaxy. So earlier I mentioned Cepheus, the king, and Cassiopeia, the queen. Well, Andromeda is the princess, so they kind of go together in a way. But you're going to have to use some imagination to see these figures. Maybe a little more than imagination, actually. Yeah, representations. Anyway, the Andromeda Galaxy, as Saul mentioned, is enormous in the sky. It's so big that, in fact, that's not it. That's it. I can't actually fit the entire thing into the field of view of my telescope at any given time. Because as Saul mentioned, it's about 6 full moons across. So you can see it with the unaided eye, and very well with binoculars if your skies are dark. But when you aim a telescope at it, especially a large telescope, at first a lot of people are underwhelmed because it's so zoomed in that you're sort of just lost in the glow of the galaxy, and there isn't a lot of contrast. So to create this image you see here, I actually tiled 10 images together. So 10 pointings of the telescope mosaic together. So kind of 5 on this row and then 5 on the top row. So if we were to take a live view look at it, we would only see a very small slice. And we're going to focus first on the core of the galaxy, the brightest region here, the part that you can see actually naked eye. And in this view, you can see the core is just so bright and so obvious. There's almost no contrast there anymore. It's almost blown out. But you can see that there is a line of dust and gas. So when we looked at the Bubble Nebula just a minute ago, we saw a certain star-forming region within the Perseus arm of the Milky Way. And the Perseus arm of the Milky Way is a line of dust and gas, a lot like this, but of course, we're inside of it, so we can't see it very well. But here we're looking at a different arm in the Andromeda Galaxy, and you can see it much better. So Andromeda is a spiral galaxy, just like the Milky Way is, but we're viewing this at a slight tilt, a moderate tilt. So it's kind of difficult to perceive the spiral structure very well. And it doesn't really have very obvious arms like some other galaxies do, which we're going to look at later. But it is nonetheless a spiral galaxy. So Andromeda as a whole contains about 1 trillion solar masses worth of stuff. 1 trillion times the mass of the sun as a whole. The Milky Way contains maybe 300 to 400 billion or so, somewhere in that area. It depends on who you ask, because it's a lot harder to study the Milky Way in detail since we're in it. It's hard to see what's on the other side of the core. But here, the core is very obvious, and at the center of basically every galaxy, almost every one, we'll get to an exception soon, there is a supermassive black hole. So in the center of our Milky Way, near the direction of Sagittarius, is what we call Sagittarius A star. Star as in an asterisk. And that's our supermassive black hole in the Milky Way. And it contains 2 or 3 million times the mass of the sun. It's million, not billion or trillion, just million, which is big. It's big, but it's definitely not huge compared to other galaxies. Andromeda's supermassive black hole was one of the first black holes to be identified at the center of another galaxy. And it's in fact a topic that one of our own astronomers at McDonald Observatory, John Cormandy, worked on. And he determined its mass to be roughly 30 million times the mass of the sun. So significantly larger than our massive black hole, but much smaller than, say, some others, like the one that was imaged last year in the Virgo galaxy, which is much larger. Yeah, we're gonna take a look at some other bits here in this field of view in a moment. But Saul, back to you.
Yeah. So before we take a closer look at Andromeda, I kind of want to tell y'all a really cool thing about it. It's actually moving straight towards us. So the Andromeda Galaxy is actually on a collision course towards the Milky Way and will collide with us in about 5 billion years or so. So no reason to panic right now. And when galaxies collide, they don't collide head on. Kind of, they don't crash into each other like two cars going head first into each other, but they more merge together like two clouds of gas or two swarms of bees, kind of coming into each other, swirling around each other, and then becoming one brand new galaxy, or brand new cloud, brand new galaxy in this case. As a collision occurs, new star formation will occur due to the gas and dust suddenly kind of compressing into each other, kind of forcing new stars to be born. And they can actually be seen in this image, represented by the red pinkish areas, the bright red pinkish areas found along the arms of the image. And this is going to be lots of brand new stars. And as the galaxies merge more and more together, they will slowly start becoming more of a general blob instead of having their own spiral shape. And eventually, their cores will combine, creating a brand new galaxy known as Milkdromeda. Now, personally, I'm not the biggest fan of that name, but we have 7 billion years to come up with a better name. And kind of speaking of those bright areas of star formation, there's actually one we can see right now in the Andromeda Galaxy, which Stephen will point out.
Yeah. So before I talk about that star forming region, I did want to provide a quick weather update. I am keeping my eye on it just in case it does clear up and get some live views for you. It is still very cloudy, but we do have Mars at least poking through. So there is some hope, but we should be seeing a lot more stars there. So it's still very cloudy and hazy, but conditions are changing very quickly. But I also want to point out that temperature. And yeah, this dome is not heated, so it's cold. But yeah, we're going to talk about a particular spot in Andromeda, which I find absolutely fascinating. So we talked about the core, and if you follow these lines of dust, trace them all the way down here to the corner, and I'll make this full screen for you guys. All the way down there, you get this bright bluish patch. And if you look carefully, some kind of over here, you can see some slight pinkish regions, kind of like what Saul was talking a bit when our Milky Way and Andromeda merge, we'll have lots of star formation. There is star formation going on in Andromeda, but not nearly as much as there will be when we merge. Oh man, I don't know if you could hear that through my mic, but the whole dome was just shaking from a huge gust of wind. So it may actually be even too windy to open the dome safely. But anyway, this area down here is known as NGC 206. It's bright enough and obvious enough to get its own designation separate from Andromeda, although it is in fact part of the Andromeda Galaxy, M31. And what this is a region of very massive bright stars within Andromeda. And this is really something special because ordinarily, when you look at an image through any telescope, if you see an individual star, like say this star here or this star here, what you're seeing is a star in the Milky Way in the foreground, much closer, maybe a few thousand light years or so away. But not this time. This is one of the few places where, with an amateur telescope, you can resolve stars in another galaxy. That's no easy feat at all. That's really tough to do, but these stars are so bright that you can. Now, there's lots of other stars too in this kind of hazy region and within the dust, but they're so faint and so far away and so close together, they just become one diffuse glow. And that's the same story with the Milky Way in the sky. That's why it's called that. That milky glow is in fact millions and billions of stars so close together, so far away, and so faint that to our eye they appear as a faint fuzzy thing. But even in a telescope, we can't resolve all of the stars here, except for these, because these stars, by and large, are O and B class stars. Like we saw in the Bubble Nebula, we saw what just one of them could do. If they're really big and bright. Now we have hundreds of them all in one big cluster. And so this is an area of recent star formation, and a lot of it. This massive cloud. We call areas like this OB associations, O and B class stars. And it's one of the biggest and brightest in the local group, if not the biggest. It's just enormous. If you were on a planet, are orbiting one of these stars, well, you'd have a bad time because those stars are really hot and you probably wouldn't be habitable. But if you could survive, the night sky would be incredible because there would be so many other bright stars in the sky from within that cluster that the night may not actually get very dark. When your sun sets, there'd be so many other giant stars in the sky, you could probably still see just fine. So yeah, that's NGC 206. One of the few areas an amateur telescope can resolve stars in another galaxy. But Saul, going to turn it back to you.
Yeah, so kind of going back to the topic of galaxies, the Milky Way and the, well, better yet, the Andromeda Galaxy isn't the only galaxy close to us. The Milky Way and Andromeda Galaxy are actually part of what's known as a local group, a galaxy group that contains more than 80 galaxies. Oh, press the
There you
one
go.
button. Yep, there it goes. Yeah, so here's an image of the local group we are currently in. So here at the center is the Milky Way. Over to the top left, we got Andromeda. And you might also notice there's a bunch of little dots scattered about through here. So the majority of the galaxies in our local group are what we call dwarf galaxies. So a dwarf galaxy is a very small galaxy, being made up of only up to several billion stars, instead of hundreds of billions of stars, like the Milky Way or Andromeda Galaxy. And there are actually two very famous dwarf galaxies that we call the Large and Small Magellanic Clouds. So these two dwarf galaxies, well, more specifically, here are the Large and Small Magellanic Clouds. The one in the top right is a large Magellanic Cloud. It's actually visible to the naked eye, but in the southern hemisphere. So sadly, it will more likely never be one of our targets, unless the whole planet just flipped upside down. We're suddenly in the northern hemisphere. But there will be a lot of other situations regarding that. But these dwarf galaxies actually make up over half of the galaxies in our local group. And we're actually going to take a look at one of the dwarf galaxies, but one visible in the northern hemisphere. Back to you, Stephen.
Yeah, by the way, if any of you have seen the large or small Magellanic Clouds for yourself, be sure to let us know in the comments, because that's something I've never done, because I've never been that far into the southern hemisphere before. But it's something I wish to do, is to see those for myself. I wish we could see them from here, but unfortunately, not going to happen. Even no matter how late I stay up, never going to happen. But we can see some other dwarf galaxies, like this one here, M32. It's another companion to Andromeda. And this one down here, M110. I'm going to focus more on M110 because I think it's the more interesting of the two. But both of these are not only dwarf galaxies, but they're also known as satellite galaxies. And that's because they are in orbit around Andromeda. So not only are they smaller than the average galaxy, but they are going around Andromeda just like a moon goes around a planet, or the sun goes, or I'm sorry, the Earth goes around the sun because the sun's the bigger thing. Small galaxies can go around larger galaxies. And that's the case with M110 pictured here. And M110 at first looks rather unassuming, but it is somewhat unusual. It is classified in several different ways. It's a dwarf galaxy, right? Smaller than the average galaxy. In this case, about 10 billion times the mass of the sun as a whole, whereas Andromeda is a trillion. This is only 10 billion, so it's much smaller than Andromeda. It's a satellite galaxy. That's its second designation. It's an elliptical galaxy, meaning it is a kind of egg-shaped. And if you've tuned into previous programs where we looked at elliptical galaxies, you'll know that they are kind of red and dead as in general. They don't have a lot going on. They're made mostly of older stars, which are smaller and lower mass. And you don't see those bright star-forming regions in them. You don't see a lot of dust. Except this one is also classified as a peculiar galaxy. And I'm not just calling it names. That's its designation. It's a dwarf elliptical peculiar galaxy. What makes it so peculiar is because, unlike almost all elliptical galaxies, it has dust in it, right there in the core. And when you see dust, that's often means it has the ingredients to form stars, but it's not. And oftentimes we don't see a lot of dust around the core of an elliptical galaxy. That is rather peculiar. It's not common. And how it got that way, not entirely sure. But the the history behind this galaxy is probably that it started out a lot bigger. Because oftentimes with satellite galaxies, they are in orbit around their larger galaxy, but as they go around, the larger galaxy kind of steals some of its stars and material, or they kind of get strewn out, and they slowly kind of evaporate or erode away over millions and billions of years until there's just the core group left, or they completely merge into the larger galaxy. That's the case with other dwarf galaxies and satellite galaxies. The Milky Way has done that, we think, to other satellite galaxies that got a little too close. It basically ate them up and swallowed them. So not all the stars in the sky actually formed in the Milky Way. Some of them probably formed in another galaxy and that merged with the Milky Way. But likewise, this galaxy probably was bigger in the past, but it's lost material. And so maybe it was a more conventional galaxy in the past, but the remnant that's kind of that remains for us to see, it makes it look more peculiar compared to other similar sized elliptical galaxies. But zooming out again, the similar story with M32 over here, and that will probably merge into Andromeda sooner than M110 down here. But all right, we're going to transition now away from Andromeda to the other little brother of the local group. So back to you, Saul.
Yeah, so let me introduce our next target, which is one of the other big galaxies in our local group, known as M33. So M33 is not that much further away than the Andromeda Galaxy. It's known as a Triangulum Galaxy, and it's about 2.7 million light years away from the Milky Way, and about 750,000 light years away from Andromeda. And actually, from observations we've seen that the Triangulum Galaxy is actually moving towards the Andromeda Galaxy. And some evidence suggests that they might have even had a small collision a few couple millions or 100 million years back. And some models show that once Milkdromeda is created, the galaxy when Milky Way and the Andromeda collide, the Triangulum Galaxy will orbit the new galaxy that was created. And kind of to get a better look at the Triangulum Galaxy, I'm going to switch it back to Steven.
Yeah, so back to our map of the sky, and you can also see the real sky down here, and you can see not a lot of stars, basically just Mars shining through just a little bit, but not really enough to get anything, unfortunately, at the moment. Just a few sucker holes that won't stay there very long. But yeah, we're going to look at a previously taken image of M33, the Triangulum Galaxy. And of course, the Andromeda Galaxy is called that because it's within the constellation of Andromeda. The Triangulum Galaxy is called that because it's within the constellation of Triangulum, which is a triangle. This little triangle here. And it's actually a little bit above it, but it's still, we consider that within the bounds officially of Triangulum. Triangulum, I've always thought, is kind of a silly constellation. It's a triangle. If you pick any 3 stars in the sky, it doesn't matter what 3, but I guarantee you can make a triangle out of those 3 stars. But these 3 stars in Triangulum are the only ones officially recognized as a constellation of a triangle. It's actually meant to be the measuring thing, like an angle. It's a measuring device rather than just the shape and abstract. But it's up there, and here is a previously taken image of it. This is, I have to confess, not my best image. The conditions that night were not great, but we'll make do. I haven't had a chance to retake it. But M33, or the Triangulum Galaxy, is, like Saul said, another member of the local group. It's the little brother, you could say. So the Milky Way, 300, 400 billion stars-ish. And Andromeda is maybe 1 trillion solar masses worth of stars and stuff. Whereas in comparison, M33 is pretty small. It's 50 billion solar masses, as opposed to 1 trillion for Andromeda, or 10 billion for M110, that little satellite galaxy we just saw a minute ago. So it's small, but still substantial on its own right. But it is, despite being small in mass, it is relatively large in the sky. It's still bigger than the full moon, and I can't quite fit it all into the field of view in this telescope. As you can see, I'm kind of cropping a little bit of it out. But there's a lot of interesting things about Triangulum that make it kind of special. I mentioned before that almost every galaxy has a supermassive black hole at its center. Almost every galaxy. The Triangulum doesn't, and that's sort of weird. And there's some debate about what that really means, because there's debate about what really comes first, the supermassive black hole or the galaxy around it. It's kind of a chicken and an egg problem. But clearly, you don't have to have a supermassive black hole to form a galaxy. They may play a role in the evolution of the galaxy, but it is a small role, because even the largest supermassive black holes pale in comparison to the galaxies that surround them as a whole. So they're a relatively small portion of the mass. But in this case, there isn't one really, we think, at all, that at least we have any strong evidence for. So that does make it rather unique and puts it into a rarer category. But what makes Triangulum also rather unique is that it is a starburst galaxy. When we looked at Andromeda, there were a few pink regions and a few blue stars, like we saw in that little cluster. But they're just everywhere in M33. M33 is full of star formation, just all over the place. We got lots of blue, massive stars strewn in these spiral arms. And up here, we have an incredibly massive star-forming region. When we looked at the Bubble Nebula, we saw that pinkish red color. There it is again, but an even larger star-forming region. Because this is 2.7 million light years away, and it's still very bright. And in fact, I like looking at this particular spot with a really large telescope visually, especially like our 82-inch telescope here at McDonald Observatory. With an eyepiece on that, and you look at that little area, you see a tremendous amount of detail. And I have a Hubble Space Telescope view of just that particular region in false color. This is with a specific filter to only look at hydrogen in more contrast. So it's a different color way of representing the data. It's false color, but the structure is all real. And it's just this wonderful knot structure. Some people call it a galactic knot, the K. And it's a massive star-forming region, one of the most massive we know of. It's about 6,300 times brighter than the Orion Nebula. And if some of you I'm sure, are familiar with the Orion Nebula, but if you're not, it's one of the most famous and brightest star-forming regions in the sky. And it's also something you can see easily with, say, binoculars or a small telescope. Any telescope can see that. But this is 6,300 times brighter. So if this were in our own galaxy, it would just be incredible. It would just be an unmistakable object in the night sky if it were within the Milky Way instead of this other galaxy, M33. Another interesting thing about M33 is, although it, like Andromeda and the Milky Way, is a spiral galaxy, you can kind of see that the spiral shape is much more subtle, much lower contrast, and much more diffuse. It is a very diffuse and spread out galaxy as a whole. But it's still classified as a spiral galaxy. It just goes to show that there's a lot of variety in the shapes and sizes of galaxies. But yeah, there's another awesome object. Some people say that they can see this with their naked eye. Some people say they can see the Triangulum Galaxy without a telescope at all. I think I've done it once or twice, but it's really tough. But if you can, then technically that's the most distant thing you can see without a telescope, just looking up. But depends on how good your skies are and how good your eyes are. And I don't know if my eyes are quite up to the task. Maybe I've seen it once or twice. But all right, Saul, back to you.
Yeah, that's super cool. I didn't know you could see it with the naked eye.
It's tough. Yeah, give it a try next time. It's clear. It's a challenge, though.
Yeah, gotta try it. So, kind of introducing our last target for the night. So, we looked at things in the Milky Way, we looked at things in the local group, and next we're going to look at something even further away than that, a galaxy known as NGC 7974, which sits at about 105 million light years away. Now, to put that distance into perspective, let's compare Earth to this distance in this age. So the mountain the observatory sits on formed about 35 million years ago. The dinosaurs went extinct about 65 million years ago. The light we're receiving from this galaxy is even older than that, as old as the Jurassic period here on Earth. And this galaxy is what we call a barred spiral galaxy. So the reason I say it's a barred spiral is that apart from the three main categories of galaxies, elliptical, spiral, and irregular, you can say that there are types of subcategories. So for spiral galaxies, there are spirals, which you can see here in the graph in the top row. There are intermediate spirals, which are in the center, and then barred spirals, which are lower down ones. These are more anything help us know more about kind of like the shape of the galaxy and give it an easier identification. And to get a better view of it, or kind of to get a better idea of how a barred spiral galaxy will actually look like, Steven has an image of that.
Yeah. So, well, first I want to show you where it is in the sky. Yeah, it's located in the constellation of Pegasus. And we're going to look at the particular barred spiral galaxy NGC 7479. Pretty high up right now, just a kind of in the southwest, but high, almost straight up from where we are right now. Again, previously taken image rather than live, but here it is. NGC 7479 is, I think, one of the most beautiful galaxies in the night sky, and it's also one that I think is often overlooked because it is kind of small. You kind of need a bigger telescope to see it. But I love that shape. Some people call it the Superman Galaxy. I don't think it's a nickname that's really stuck, but I can see why they call it that. It kind of has that nice S shape to it. And it is, as Saul mentioned, a barred spiral galaxy. So there is the bar going across, and then you have two very obvious spiral arms. And I see we have a question about it. What is the magnitude of this galaxy? I believe it's magnitude 9.5 or 10 or so. So yeah, that's for the astronomy nerds. This is a really nice shape to it, and it may owe that shape to an event in its past, maybe a few million or 100 million years ago, where a satellite galaxy or dwarf galaxy likely merged with this galaxy, and that sort of distorted its shape just a little bit. Not quite as dramatic as a merger between the Milky Way and Andromeda will be, which will completely transform them. But this was a much smaller galaxy merging with a larger one, and so it just twisted its shape a little bit. But again, 105 million light years, so it's a healthy distance, but it's surprisingly bright for that distance. I also want to point out in the background there are some little tiny fuzzy things, right? So all these are stars in the Milky Way, but these little fuzzy things are background galaxies, which may be hundreds of millions to billions of light years out. And wherever you look, you're going to see galaxies. Again, this is outside of the local group, and there are trillions of galaxies out there, so it could have picked any number of different galaxies that are up right now to highlight. I highlighted this one as just one example of one that's outside the local group. that happens to be pretty and in a good location in the sky. But again, our local group, the Milky Way, Triangulum, and Andromeda, and the other 77 or so little dwarf and satellite galaxies mixed in there, are all generally gravitationally attracted to one another. And that's really defines the local group. That in general, those galaxies are merging towards each other. But if you look out beyond that, beyond the local group, like this galaxy, it's moving away from us. It's moving away. That's because of the expansion of the universe. Basically, space itself is expanding, creating more space in between us and these galaxies. And so they're, in general, moving away from us. And so the further away you look, the faster they appear to be moving away from us as well. In other words, astronomers would say they're being redshifted, whereas the local group, they're being blue shifted. But yeah, this is just one example of countless galaxies. We've looked at a lot of galaxies before in this program. We're definitely going to look at a lot more later on. But I like to kind of keep our local group in mind, to try to put things into context, because just like the Earth goes around the sun and we have our solar system, and the solar system goes around the center of the Milky Way, and the Milky Way is within the local group. It's kind of the next stage up in our neighborhood of things. And it's something I always think about when I think about the grand scale of the universe is, how does our local group compare to what I'm seeing? Gives me some perspective. But I think that's where we're going to start wrapping up the program. If you have any questions for us, Saul and I are going to take turns answering some of those questions. And also our moderators are going to try to take a few of them as well, if we don't have time to get to them. But Saul, do you see any questions in the chat that you'd like to tackle?
Yeah, actually. So I might be misreading this one, but it's from Charlie Ondrej. The question was, the graphic showed the Milky Way, but it was referring to the one of the local group, as the center of the local group. Probably just an easy way to show the local group. Question, is the local group orbiting a single point? So here's the image again of the local group. And the center in this image, the Milky Way being in the center, actually isn't because of it being the center of gravity. The actual center of gravity of the local group actually lies somewhere between the Milky Way and the Andromeda Galaxy. So kind of around this area is where most of the objects are orbiting around.
All right, so I did see another question I'm going to tackle. Charlie asks, what is my favorite time of year to view the night sky? When it's clear and when the moon isn't up. There's always something interesting up, and the winter, despite being cold and kind of brutal sometimes, has all manner of interesting things. And frankly, I can't pick an easy favorite in terms of what's up. I can only pick a favorite in terms of weather, and I guess that would probably be the fall, October-ish, November-ish, and period that just ended, because it usually is pretty calm and clear, and there's a lot of variety of things that are up at this time of year. But if you ask me that again in spring, I'll probably say spring. And if you ask me that again in the summer, I'll probably say summer. Whatever is up right now, I love, honestly. There's never a clear best time because there's always something interesting up there. So I got another question for you.
Yeah, so actually there's one here that I feel will be better for you.
Oh, okay.
Up. See, it's from Dan Janosik. Sorry about that. Got a bit tongue-tied there. And let me pull it up here so the others can see what it is, if it lets me.
No?
Oh wait, apparently it got lost. It wasn't from that person.
Okay.
Oh, no, it is. It is. Yeah. So here it is on screen.
Oh, okay. So Dan asks, "What is the?" I'm not sure. I'm not sure what exposure you're referring to, but in general, if you all my pictures are between 2 hours and 10 hours for tonight. The one of NGC 7479 pictured here, this was about, I believe, about 10 hours worth of time. And that is 4 hours of luminance and 2 hours red, 2 hours green, 2 hours blue. All right. If you got another one you want to tackle, Saul? If you see one.
That one's from Miles Groff. Do we have any theories on where the universe is expanding to? Does the expansion of the universe ever slow down or speed up? So originally, some theories were that the universe had a kind of an edge to it, and that space would just keep on expanding to a certain point until then it will all kind of snap like a rubber band, or something that was actually known as the Big Crunch. Now, more recently, from observations we've had, we've actually seen that that doesn't seem likely. From what we know, the universe is expanding. It's actually getting faster. There are currently no real signs of it slowing down, and will probably expand infinitely. As far as we know, there really is no edge or limit to how far it can expand. And Steven, do you have anything to add to that?
No, I mean we're trying to figure out exactly why the universe is expanding here. It's one of the largest projects here at McDonald Observatory. We're doing with the Hobby Eberly telescope, and we have a press or a news article you could read on our website about how that project works. I want to tackle this question by Roger I. He asks, what is just beyond the local group, or what other local groups are there near ours? So there is, just beyond the local group, there are a smattering of galaxies. Some people call it's like the Big 12 or something, where there's a few other larger galaxies, some of which we've looked at before, that are kind of in the range of 5 to 15 million light years out. But in general, the next real definitive thing that we organize it at is the Virgo cluster, or the Virgo supercluster sometimes. And back in the spring, I talked a little bit about the Virgo cluster. I believe that was in April or May, when that part of the sky is better situated. And so, that's basically the local group, the Virgo cluster, Virgo supercluster, which includes some other things. And beyond that, it gets kind of arbitrary in how you define it. But generally, when you look at the very, very, very large scale of the universe, you tend to find galaxies clustered into groups, and those clusters or groups are kind of strewn about in strands that look kind of almost like a web. Some people call it the cosmic web. But yeah, that's you can continue dividing it almost endlessly, however you want. Yeah.
So here's one. Erica Heinen. Where's the best place in Texas to see the Milky Way with the naked eye? Darkest natural sky. So a little fun fact, the McDonald Observatory is in an area that's considered to be some of the darkest skies in the continental US. And Steven probably has some more stuff he can add to that in terms of how dark it actually is.
Yeah, so we do have some of the darkest skies anywhere, not only in Texas, but in the United States. And we want to keep it that way. So McDonald Observatory is working with several other parks and conservation agencies and groups to create what we call the Greater Big Bend International Dark Sky Reserve. So in terms of what measurably is the darkest place in Texas, it would be down here in Big Bend. And we're not that far from there. It's still very, very dark up here where McDonald Observatory is. But we want to create an area that is essentially where the night sky is going to be preserved in its natural state for future generations, and for the purpose not just of for science like we do here at McDonald Observatory, or just for looking at, but because it also benefits the environment. Light pollution affects animals and insects a great deal. So it's healthier, and it also helps that better lighting designs, night sky friendly lighting designs, are safer and cheaper as well. So that's kind of a project that me and several other people are working on, is creating and certifying this through the International Dark Sky Association. I am also proud of the fact that this will include lands in Mexico as well. So it will be an international dark sky area, protecting it for future generations. It's a great question.
Yeah.
Let's see, we got
Actually,
yeah,
sorry, a question that came up related to that from Dan Janosik was our Bortles sky rating?
two.
2? Nice.
Two. So we got quite a few other questions here.
Yeah, I
Uh,
found one from Barry Allen. Of the dwarf satellites, galaxies gravitationally bound to our Milky Way, do we have an idea of the larger ones and what kind of gravitational influence they might have on smaller ones? So we do know several galaxies are orbiting the Milky Way. We refer to them as satellite galaxies. And usually what occurs is they might continue orbiting the larger galaxy, or something that may occur is that the larger galaxy, so like in this case our Milky Way, might devour the smaller galaxy, and what's referred to as galactic cannibalism. So a very fun, if you want to have a new fun space term, there it is, galactic cannibalism, of the larger galaxy eating the smaller one. And with that being pulled in, then new star formation will occur in that area, and there will be one less dwarf galaxy.
yeah. Here's another interesting question. Can you explain how was identified the new fossil galaxy found in the Milky Way? I believe you're referring to one that if it was found recently in the last couple of years, because there's actually been a few. Uh, uh, One that was discovered by data from the Gaia Space Telescope, at least preliminary. That's how it was done. So what the Gaia satellite does is it scans a huge area, most of the sky, and it looks at all these different stars within the Milky Way. It's really just focused on the composition and structure of the Milky Way, and it looks at how bright they are and roughly what their composition is and how they're moving. And the way you tell like a fossil galaxy, like the remnants of another galaxy that merged with the Milky Way, apart from everything else, is that generally those stars are going to have the same composition, meaning they're going to have the same amounts of metals in them, things that are not hydrogen or helium. It's going to have this. Generally, those stars, if they form the same place around the same time, will be compositionally similar. And they'll all have a similar motion through the galaxy. They'll all be kind of still traveling in one general group. So by teasing out where the stars are, how they're moving, and what they're made out of, we can kind of find these fossil remnants of other galaxies that merged with the Milky Way. There's a lot of work that goes into that, some of which is done here at McDonald Observatory, determining the compositions of stars to tease out their origins. It's actually a big project with the 107-inch telescope here at McDonald Observatory. We've got time for maybe a couple more questions. So if you want to tackle one more.
Let's see. Trying to see which ones I would know the answer to for this. Here's a pretty interesting one. I think we can both do it. From Dan Janosik, what are your thoughts on ground-based astronomy and the effect of satellites and astroimagery? So kind of like to just start off with, ground-based astronomy is very useful. So the idea usually is if you can get a satellite to space, you'll get a better result. But that costs a lot of money, a lot of resources, and if something were to go wrong, there's not really a way to fix it. So with the James Webb Space Telescope, once it's going to be sent out there, it actually has to unfold itself. And there are many things, if memory serves me right, about 23 different things during the unfolding process, that if one of them were to get stuck, it'd be done. James Webb Space Telescope would be unusable and there's no way to actually go and fix it. So kind of like on the subject of the effect of satellites on astroimagery and also the ground-based astronomy, we do have, the issues of weather and satellites might be going by, or kind of one of the more recent things that come up have been Starlink, the Starlink satellites. If you don't know what Starlink is basically a system deployed by, Elon Musk to try to get global internet. But these satellites, there are many of them, and they can be very bright. And if your timing's bad, could actually interrupt your research and your observation.
Yeah, so here's an example of, like Saul mentioned, Starlink passing through the field of view of the telescope. What that looks like is just a line going through. And you can see that, yeah, it's kind of annoying. You have this streak. There are techniques to compensate for this with astroimaging. If you take many images and average them together, you can average the streak out because it'll only be in one image. It's only going to pass through for a moment. So its effects on astronomy will be varied, and it depends on the kind of science you're trying to do. And we're trying to determine exactly how much that will impact specifically us at McDonald Observatory. But ground-based telescopes are still, they're not going to go anywhere. They're still definitely worthwhile because they're easier to fix. You can build them much larger than you could ever put a telescope in space, and you can update them easily as time goes on. So ground-based astronomy, it's not going anywhere anytime soon. There's still quite a lot of life left in it. And I'm gonna tackle just one more question. Let's see. Related to the, sort of this, have you ever been able to track or observe meteors and/or their entry to the planet? Yeah, so there are always meteors following, and for the most part, it's kind of unpredictable. We can say, like, oh, during a meteor shower or something, there's a higher chance of a meteor occurring during this time frame, but we cannot say it's going to be in this part of the sky or over there. It's mostly luck. One of the things I find really interesting about the Hobby Everly Telescope Dark Energy Experiment is that it has this really big field of view. And that means you have a better odds of catching meteors. And it's really difficult to get not just an image of a meteor, but a spectrum of a meteor, if you think about it. Because if you want to take the light of an object and break it apart, you have to basically look at it at just the right time. You have to know exactly where it is, and it has to be fairly bright. But the point of taking a spectrum of something is you can learn what it's made out of. Get a lot more than an image will ever tell you. Well, the Hobby Everly telescope, it's big. It's one of the largest telescopes in the world, so it gathers lots of light, which means it can pick up very faint things, and it can get a spectrum for several thousand points on the sky simultaneously. And it wasn't built to hunt for meteors, but as it turns out, it's a great meteor hunting machine. And just by chance, every now and then, a meteor will pass through the field of view while we're trying to observe something else, photobombing it, but we'll get some great data out of it. And in fact, there are some astronomers at McDonald Observatory are using that data to try to learn more about how meteors form, exactly the characteristics of it while it's burning up in the atmosphere. So hard to track, but sometimes we just get lucky. We can learn from that. I think that's all the time we have for tonight. Thank you all for joining us on this cold and cloudy night. I'm sorry the weather just didn't really cooperate. But that's often the case in the winter time. Is the weather just is really hard to predict. So it happens. But thank you all. Thank you, Saul, as well, for joining me tonight, being my co-host. You're fantastic. And thank you to my moderators as well in the chat for helping us out. Yeah. All right. Take care, y'all. Clear skies.